Hello, I'm Justin Donay, and with me today are Cameron Chappell, Aaron Lomas, and Joe Miceli. We will be presenting an analysis and comparison of a diesel generator and a concentrated solar power station for our thermodynamics class with Dr. Vasquez at the University of Nevada, Reno.
My name is Cameron Chappell, and in this presentation we will be discussing the diesel cycle, which includes the ideal compression ignition process, calculations of that process, the application of it, and then Justin Donay and Joe Miceli are going to discuss the solar thermal power generation process, which includes the heat process and the Rankine cycle, and then we will conclude with a comparison. So for this project, what we wanted to do was replace the Tracy power plant, which produces 1,021 megawatts of power at peak power output, and we want to replace that with either a system of diesel generators or a system of solar thermal generation. And we're going to look at some of the pros and cons of each process in terms of cost, mobility, and footprint, and go from there. So the difference between the diesel cycle and the Otto cycle is that the Otto cycle runs off gasoline and it's a spark ignition system. So with the Otto cycle, what we have is an air-fuel mixture in the cylinder before it even starts compressing, and what makes it actually ignite is a spark ignition. Whereas with the diesel cycle, we compress the cylinder first, get the air to the combustion temperature of the diesel, and then inject the diesel with a fuel injection system. So in step 1 here, that's the compression stroke. It's an isentropic compression. Then we move to step 2. After this air only, has been compressed, it's to the combustion temperature of the diesel, and then diesel is injected, and that's called the power stroke, which is where we get the power out. In step 3, which is the exhaust stroke, there's an isentropic expansion of the gas, and then it's released. And then in step 4, it's isochoric, so the volume stays the same, and this is called the intake stroke.
Hello, Dr. Vasquez. My name is Aaron Lomas, and I'll be discussing the following 4 slides of the diesel portion of this presentation. First, assumptions. To reduce the analysis to a manageable level, we made the following assumptions. The first assumption, mean effective pressure. In our research, we found that the mean effective pressure for diesel engines varied between 1.4 and 1.8 megapascals, so we chose that ours is 1.6. Second, we decided that our engine would run at 1500 RPMs, which again is a reasonable assumption for a diesel engine. Now, given cold air standards, we made our assumption for a cutoff ratio of 2 and a compression ratio of 16. Our K value is assumed to be 1.3. We felt that the highest temperature of our working fluid would be the peak flame temperature of diesel, which is 2,327 Kelvin. Also, we felt that our temperature prior to the ignition, our temperature of our working fluid prior to the ignition of the diesel would be the ignition temperature of diesel, which is 483 Kelvin. As mentioned, we applied all cold air standards and also assumed in our calculations that we were working with a closed system. Also, in keeping with cold air standards, our ideal gas constant is 0.287 kilojoules per kilogram Kelvin, and density of air is 1.225 kilograms per meter cubed. On this slide, we have the temperature and pressure for each phase of our 4-stroke power cycle, as well as our specific heat at constant pressure and specific heat at constant volume and our revolutions per minute, or cycles per second. We felt it was important to have these values early on in our analysis because they will be used in the majority of the equations, which I will be discussing on the next slide. The following equations were used in our analysis with the goal of being able to describe a diesel engine that could produce a power output of 1,021 megawatts. By finding Q in and Q out, we were able to solve for our work, which we could relate back to power through our mass flow rate. Also, with these values, we were able to solve for the displacement of our piston head, and we also checked our efficiencies by solving for the Carnot efficiency, which is the best possible efficiency, and also the diesel efficiency, which would be a major clue to the accuracy of our calculations if we were to find that the diesel efficiency is greater than the Carnot efficiency. The results of our analysis are as follows. Qin of our diesel cycle is 1853.22 kilojoules per kilogram. Qout is 907.35 kilojoules per kilogram. With these values and thermal efficiency of our diesel cycle, we were able to find our displacement, which is the end goal of our analysis. The total displacement necessary to produce 1,021 megawatts, given our assumptions, is 35.27 cubic meters. This translates to a volumetric flow rate of 880 meters cubed per second at 1500 RPM. To give some visual perspective, an Olympic-sized swimming pool is 2,500 meters cubed. So at the calculated rate, our engine exhaust will fill an Olympic-sized swimming pool every 3 seconds.